Okay, when we're looking at energy in collisions, energy may not be conserved in terms of keeping the energy kinetic. In a crash, so you might have one object crash into another object, the kinetic energy may change. Okay, so you may have a change in kinetic energy, and that means we get other types of energy released. So there might be some sort of heat given off in the collision. Now, if there is heat and stuff given off in a collision, we call it inelastic. The total kinetic energy before does not equal the total kinetic energy after. And remember, unlike momentum, it's not a vector, so there is no negative signs for direction. If, however, the kinetic energy is conserved, which is hardly ever. I mean, in reality, you can't have a collision that doesn't have any sort of energy transfer as such. We do say that things like gases and so on, they do collide ideally with no change in energy, but in this case, it's not likely. So heat will be generally always given off, but if effectively it's the same energy in kinetic before and kinetic after, it will be an elastic collision. Another thing you can use, if it is elastic, this is only for elastic collisions, then speed of approach is equal to the speed of separation. Okay, remember, speed is not the same as velocity. In this case, before a collision, these two masses are coming towards each other at 15, so 10 plus 5. Afterwards, they need to be separating at the same rate if it is elastic. And so they are. The one that's going left is 8, that one's 7, so 8 plus 7, that means they're going away from each other at 15. I don't know why I've got 10 and 5 there, it should be 8 and 7. That could happen for any sort of motion. This one here could actually be going to the right at 2, so that means this one will be approaching this one at 8, and that means afterwards must be 8, so it could be, this one might be going at 7, and this one might be going at -1, something like that, okay? And here's a similar one, so we've got 10 and going this way, 5 going this way, so it's approaching at 5, okay? And then the afterwards must also separate at 5, so if we've got one going at 13 there and 8 there, this one's leaving this one by 5. That maths there should make 5. So we can work out this one. What's the mass of the wagon? So total momentum before, total momentum before must effectively be the same afterwards. So total momentum before is going to be 4,000 times 3.5. That equals 1,400. Now, afterwards must also be the same. So if they move off together, the masses are going to combine. So we're going to have 4,000 plus the mass of the wagon times our velocity of 2 will all be equal to 1,400. Oh, hang on, that's 14,000, isn't it? So, what do we get for M? We get M being 7,000 kgs. Now, is the kinetic energy conserved? So beforehand, it's going to be half times 4,000 times 3.5 squared, and that will be equal to 24,500 joules. And then afterwards we've got to then do, half times 7,000 times their speed of 2 squared. And that gives us 14,000. So in fact we've actually lost almost over about 10,500 joules of energy to heat or sound.